So hi, my name is Denny Bromley. I'm here with Vidya Setlur from Tableau Research, and today we'll be talking about quantifying semantic labeling of visual features in line charts. So when you're doing data analysis, it's nice if a tool can help you out to understand what's happening behind an event. For example, it'd be great if a tool could show you something like this. After a 6-month gradual rise and a bumpy plateau, the stock price tanked, losing more than 75% of its value before beginning a slow, year-long struggle that eventually only recovered 25% of the lost value. So there's a lot of stuff going on here, right? There are references to previous events, there are judgment words like only recovered 25%, there are temporal words, there are specific quantitative words, and there's also word choice, where the words that are chosen like gradual and tanked imply a certain numeric connotation, and this is where we decided to focus on. And so we decided to look deeper at this notion of quantitative semantics, or specifically, how do we leverage the descriptive and engaging power of natural language while maintaining the quantitative precision of the data. So we built a tool, and we handed it out to some people, and in this tool, people drag a word from the left over to the right, and what they're doing is they're labeling these shapes for us. And it turned out that we got a lot of data from this. We had 67 participants, we had almost 2,000 different annotations, and almost 120 annotations per chart. So there was a lot of overlap, which was actually really cool, which we'll discuss later. And this data is all in the supplementary materials, so we'd love it if you want to take a look at that. Specifically, what then we did is we took sort of a DSP-style approach where we discovered shapes in new signals by cross-correlating them with a user-labeled shape. So we take the user-labeled shape, scrub it past the new signal, and look for the low-error regions. Given this, we were able to find shapes in our signals. So we found areas that were labeled as growing or tanking or decreasing or flatline. But because of all the overlap and because of the words that were co-labeling these specific regions, we were able to go deeper than that. So we started looking at word co-occurrence. So for example, escalating typically co-occurred with increasing and rising and taking off. And plateau typically co-occurred with flatline, stable, stagnant, steady, words like that. And from there, it was sort of a short hop to do word clustering. And when we did word clustering, we found words that had pretty intuitive groupings like up and down and stable. We also found other words that sort of had these notions of soft and sharp associated with them. And because we did hierarchical clustering, we were able to subdivide these. So we found words that were sort of gently taking off, gently down or steeply down, or gently up or steeply up. And so we got to sort of begin to look at sort of a semantic hierarchy and the idea of hyponyms and hypernyms. Also in stable sort of divided into this notion of consistent versus actually literally flat. Once we did that, we said, well, let's look at individual words. And so for example here, somebody dragged the word stable to a flat region. And we can say, okay, well the slope of that particular segment is flat, is zero slope. And so I wonder what the average slope of all the segments that were labeled with stable were. And we can do this for every word. And so if we look, we can actually take a look at the average segment slope of the words, and then we can discover that actually there's some signal that pops out of this. So we can see that, for example, the segments labeled with tanking were the steepest segments. And as we go up along this continuum, we move from tanking to descending to diminishing to slumping to subsiding, up through flatline and plateau. And moving along, we see accelerating and increasing and taking off all the way up through soaring. So it was really good for us to see that we could actually pull the signal out. And so after looking at signal words, we decided to look at word combinations. And so here's a grid of all word by word, 2-word combinations and the average slopes of those combinations. And what was interesting is we found that one word can have an effect on the other. So for example, the average slope for the word decreasing in the previous figure was negative 1.4, but a slow decrease was only negative 0.5, so less steep. And a fast decrease was negative 2.5, so actually a steeper decrease. So slow and fast tended to act as sort of scalar operators on that original adjective. Similarly, the average slope for increasing was about 1.2, but a sudden increase had a slope of 1.9, and a gradual increase had a slope of 0.7. So again, we're beginning to quantify how word modifiers can act as these scalar operators. So what we did was we decided to sort of operationalize this a little bit. So here's a signal, and we linearized it to break it down into these different segments. And so in order to come up with these labels for these different segments, all we did was take the slope of that segment and look it up in these dictionaries that we created. And so we're able to actually use that data that we'd found to label these signals. So that's the bulk of the paper. In terms of what this paper contributed, we obtained natural language descriptions of data trends. We quantified what specific trend descriptors mean. We quantified specific univariate line slope descriptions. And we began to quantify the effects of one word on another. In terms of future work, we're looking to increase semantic precision. We want to increase semantic richness. For example, more words, more modifiers, and also looking a little bit deeper at semantic hierarchies, synonyms, hypernyms, hyponyms. In terms of applications, specifically, we're interested in, can we quantify the scalar effects of adjectives like fast and slow? Can we operationalize that somehow? Can we run this analysis in reverse to understand if the quantifying descriptors used in engineering or medical texts or similar things align with their commonly held quantitative intuition? Or are they being used to describe slightly different quantitative effects? And then also, given that LLMs are literally where language meets data, can we increase the semantic accuracy of that interaction? So with that, I'd like to say thank you very much, and if you have any questions, please contact us.